So these are some data for the applet for the centripetal force experiment. So this is called the physics Aviary, and then this will be the opening picture, and this is the table for that, and then on the next page you will find the actual experiment. But the applet is really close to what you're supposed to do in the actual experiment. So here's the table. I'm going to go to the applet in just a moment. The table also appears on the Excel sheet, and when you plug in the numbers here, it does the computations automatically, and I will show you that, but let's get started. I copied the link here, Physics Aviary for centripetal force, or I can also just type it in there. Apparently I did that before, and it gets me right there. Respectively, as I said, do the link, and there we go, either way. One thing to keep in mind here is it says that each washer that is hanging on here is 10 grams, so I'm just going to keep that in mind. I click on begin, and so there it is. And I have a number of inputs here. One of them is the washers, which is the tension on the string. So the more washers I put on here, and I can click through it, and then it does this. And it actually looks like random numbers that they give us here. With the moving mass, that's this one over here. So these up or down arrows, there we go. And you can see that the mass gets larger and larger the heavier it is, or going way back. There we go. So let's do this, 53 grams. I think these numbers are also around 53 grams. And this one here is 19 washers, which means 190 grams, which is 1.9 newtons rounded. That's the tension in here right now. And then the length here to change the length, click on this little tape here, and you also have that little tape in the experiment right beneath it. And that's pretty much it. There's the timer. I'm going to hit the start button in a moment. And sure, I'm going to pay actually attention to this one here. So this one is just beyond 40 centimeters. I'm going to call it 41 centimeters. Okay, and I have 190 grams, which is 1.9 newtons, 53 grams over here, and I'm going to pay attention to the time. The only thing that you don't have to do is you don't have to wear the same wig that Isaac Newton is wearing, apparently. Okay, so here we go, and I'm going to count the number of rotations until it goes up to 30. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. Oof, so maybe 44 after 30 seconds. Okay, I'm going to go to the Excel sheet. There we go. Oh, and by the way, the angle was 0. We saw that it was rotating horizontally. So the tension here was 19 washers, which is 190 grams, which is 1.9 newtons. There we go. And then as the piece of string there is not drooping, therefore the angle is 0, therefore the entire centripetal force is horizontal. So I multiply by cosine of 0, hence it's still going to be 1.9 newtons. By the way, what's wrong about this string being completely horizontal, that it's not drooping? Think about it. I'm going to go back here to the Excel sheet to finish that. So the mass here was 53 grams, the length here was 41 centimeters, and then I have 44 centimeters. And then it calculates with this equation. See, it's actually on the next page. There we go. These two long equations, it calculates the velocity going around and then the centripetal force. And notice that we have supplied that all in the Excel sheet, making work a little bit easier. And then when we compare this one here, the 1.8 newtons here with the 1.9 newtons here, we can see that we have a 3% error. Yeah, 1.9, 1.8, and if you give it a few more digits, then we can see that it truly is 3% here. I wrote 2 sig fig here, 2 sig fig here, because those are all my inputs. They're also all the way through 2 sig fig. Notice that the applet even though it seems to be perfect because it's an algorithm, but notice I had to count the number of rotations, so it's not totally perfect there. And this one here I had to estimate a little bit as well, right? So, yeah, perfect algorithm, but it's kind of close to the actual experiment because we also are including errors here, and the errors that you do in the actual experiment are actually somewhat larger. In this one here, I'm going to come up really close to 0% error. This one here will be, I mean, the actual experiment will be in the neighborhood of like 10, 20%, maybe even larger. All right, going to reset, change numbers of washers. There we go. Change the mass. There we go. Change the length. Let's see. Oh, yeah, the tape. There we go. All right, and hit the start button and then count the rotations. And ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 und 20. Okay, just a little bit more than 20. 20.5, let's call it 20.5. Here I was able to pause it and resume it. So 20.5 for the time, for the number of rotations. The length is, oh, what was the length actually? I forget to read that off. Okay, just short of 110. I'm going to call it 108. The moving mass is 134, and the number of washers is 27. And I'm just going to do the next one here. Pause and reset. There we go. And again, I'm going to change the length here, make it pretty long. Change the number of washers. There we go. And then change the mass here. There we go, pretty heavy. Let's see what happens. And ready, set, go. 1, 2, 3, 4, 5, 6, 7. Let's call it, I'm going to call it 7.5. The length is, oh, I keep forgetting to write the length down. 192 is the mass, and the washers are only 80 grams or 0.8. And I'm going to click on reset, and all right, just beyond 170, I'm going to call it 171 right there. There we go. And the fourth measurement. Notice this was really slow. The mass is relatively large, so this one already exerts quite a bit of centripetal force, but the tension is relatively low, so I have to rotate it slowly so that the tension can actually match the centripetal force here. All right, let's see. Some kind of other mass here. Yeah, that looks good. And some kind of other length here. Whoa, very short. Okay, and maybe a lot of, oh, I already had that lot of tension, right? Somewhere in between here. That's fine. There we go. All right, so 13 washers. 93 is the mass. The length is, looks like 25 to me, and I have to count the number of rotations in German again. So ready, set, go. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 35. There you go, 35. By the way, for me, it's actually easier to count in German than in English. The other little thing that I noticed that I like here is actually the jiggling around of the string, you know, depending on where the mass is, the string is on the right or the left. All right, let's go over to Excel. here we go. The angle is 0 all the way through for these 4 here. I had 27 washers, so that's 270 grams or 2.7 newtons. Then I had 8, which is going to be 80 grams or 0.8 newtons, always multiplying with 9.8 or rounded 10. And then I'm going to have, what was it, 13, so it's 130 grams or 1.3 newtons. And if I round this actually a little bit down, and I could say, because it's 9.8 or instead of 10, then these numbers are actually slightly smaller, ever so slightly smaller. The masses that I had here were 134, 192. This is already set in the Excel sheet as grams, so behind the scenes it's actually, I think we can see that here. Let's see it, maybe it's over here. You see the divide by 1,000 right here? Oh, that's actually off the Excel sheet of the recording. You see the divide by 1,000 right there? That's converting from grams to kilograms, so I have Excel do that for us. Okay, so the length here, the lengths that I measured were 108 here, 171, and 25, and then the number of rotations were 20 and a half. Notice the 1% error in the back, 7.5, again 1% error, and 35 rotations, and this time 4% error. Interestingly, the larger rotations yielded larger errors. Okay. Maybe that's because I didn't quite round down here. Okay, so the actual experiment is going to be larger here. You can see these here, 12, 22, 33%. These are typical results. 2% is actually relatively low for this experiment. So this is the really low percentages, differences between the centripetal force and the measured tension. Is really low for the applet, and as I said, higher for the actual experiment. So expect that, but the outcome overall should be that the centripetal force here is a measurement of the tension, respectively. The two ought to be the same within the total measurement error. All right, that's what I have here for these results.